Welcome to a 25-slide deep dive into DNS, the quiet system that turns every name you type into a working connection on the internet. Think of it as the internet's phone book. When you ask for Google.com, DNS is what hands back the actual IP address around 20 milliseconds later every single time. It's also, by some estimates, behind nearly half of all site is down help desk tickets, which is exactly why we're starting here. Over the next 24 slides, we'll move from foundations through architecture, records, operations, and modern security until you're thinking about DNS the way a senior engineer does. So let's start with the core problem DNS was invented to solve. Humans think in names, Google.com, Netflix.com, Wikipedia.org, things that are memorable, branded, and stable for decades. Computers, on the other hand, only route packets using numerical addresses like 142, 250, 190, 46. And those addresses change constantly as servers move and infrastructure shifts. DNS is simply the translation layer sitting between those two worlds, quietly reconciling them billions of times a day. Now, that translation layer didn't always exist. Back in the 70s, the entire internet, all of it, fit inside a single text file called HOSTS.TXT, hand-maintained at Stanford and emailed out to administrators every month. That worked for a few hundred machines, but by 1983, it was clearly breaking. And Paul Makapetris published RFCs 882 and 883, inventing DNS. What's remarkable is that the core standard, finalized in 1987, is still what's running today, quietly handling around 400 million domains and over 1 billion queries per second. So with that history in mind, let's see the system in action. When you type Google.com, 4 things happen in sequence. Your browser asks what the IP is, your device forwards that question to a DNS resolver, usually one run by your ISP, or a public one like 8.8.8.8. The resolver either pulls the answer from cache or goes hunting for it, and finally your device connects to the IP it gets back. Start to finish, typically 20 to 50 milliseconds. Cached, just 1 to 5. That's the whole flow at a high level. The rest of this course unpacks each step. Now, before we follow that resolver on its hunt, you need to understand the map it's working from. DNS is structured like a file system, a tree read right to left. At the very top sits the root, written as a single dot. Beneath it are the top-level domains, com, org, io, and over 500 others. Below those sit registered domains like Google or Netflix, and below those subdomains like mail or www. String it all together with that trailing dot, and you get a fully qualified domain name, mail.google.com. Every piece, all the way to root. With that map in mind, let's meet the servers that actually live on it. There are 3 primary roles, each owning one layer of the tree. Root servers, just 13 logical addresses, but over 1,700 physical machines via Anycast, point you toward the right TLD. TLD servers, run by registries like VeriSign.com, point you to the right authoritative server. And the authoritative server is where the truth lives. The actual records for a domain, hosted by Cloudflare, Route 53, GoDaddy, or whoever you've chosen. And then there's a 4th role, the unsung hero, the resolver. Your ISP, or 8.8.8.8, or 1.1.1.1, the one doing all the legwork on your behalf. Let's go zoom in on that resolver, because it's the one piece you actually get to choose. By default, you're using your ISPs, often slow, usually logged, sometimes filtered without you knowing. But swap in Cloudflare's 1.1.1.1 and you get the fastest lookups with a no-logs privacy stance. Google's 8.8.8.8 is the rock-solid global default. Quad 9 blocks known malware domains, OpenDNS gives you parental controls, and AdGuard strips ads at the DNS layer. You configure it once, on the router for the whole house, in OS settings per device, or in etc. resolve.conf on Linux, and every app benefits. Now that you've picked your resolver, here's what actually happens when it goes to work. DNS uses 2 query styles, and the difference matters when you're debugging. Recursive is what your browser does. It asks the resolver one question and demands one final answer. No excuses. Iterative is what the resolver does behind the scenes, hopping from root to TLD to the authoritative server, following referrals until it gets the record. So in any real lookup, client speaks recursive, resolver speaks iterative, and you get one clean answer back. Once that answer comes back, it's actually a record. And DNS defines over 50 different types, but in practice, 8 of them carry the load. A and a SURI or SURI A map names to IPv4 and IPv6 addresses. CNAME creates aliases. MX routes email with the lower priority number winning. TXT holds freeform text. That's where SPF, DKIM, and DMARC live. NS points to who's authoritative. PTR does reverse lookups for IP to name. And SOA holds the zone's metadata. Learn these 8 and you'll recognize roughly 80% of everything you ever touch. Now, every record carries a number alongside it called TTL, time to live, and it tells resolvers how many seconds they're allowed to cache that answer. Set it low around 60 seconds and changes propagate almost instantly, which is gold for failovers and migrations. But you pay for it with more queries hitting your authoritative servers. Set it high like a full day, and you get cheaper, faster lookups, but a bad record can haunt you for hours. The pro move? Drop your TTL a day or 2 before any planned change, then raise it back up once the dust settles. With TTLs in mind, let's trace what actually happens when you type www.google.com into a cold browser. Your browser asks the OS. The OS asks its configured resolver, say 8.8.8.8, and that resolver then walks the hierarchy. Root tells it to ask the .com TLD, .com tells it to ask Google's authoritative name servers, and only then does the real IP come back, get cached for 300 seconds, and flow down through the resolver, the OS, and finally your browser. 8 hops, usually under 200 milliseconds cold, under 5 milliseconds warm. And this is the diagram every senior engineer can sketch from memory. Now that elegant resolution path comes with a catch. The answer gets cached in 5 different places on the way back. Your browser holds it, your OS holds it, your local network resolver holds it, the recursive resolver upstream holds it, and finally the authoritative server is the source of truth. When someone says DNS isn't updating, 9 times out of 10, you're just flushing the wrong layer. So memorize these commands. Econfig, flush DNs on Windows, system resolve, flush caches on Linux and Chrome, Josh net internals, Josh ends inside the browser itself. And once you can flush caches, the next step is actually inspecting what DNS is doing, which is where these 8 commands earn their keep. And so lookup works everywhere and gives you a quick name to IP, but dig is the senior engineer's tool. Dig plus short for just the IP. Dig MX for mail records, and dig plus trace to literally watch the query walk from root to TLD to authoritative server. Memorize this syntax. When a ticket lands and the user is waiting, you won't have time to Google it. Now, running dig is one thing. Actually reading what comes back is another. Every dig response breaks into 5 sections. The header tells you whether the query succeeded, with nar being what you want to see. The question echoes what you asked. The answer is the actual record plus its TTL. Authority lists the named servers responsible for the zone, and additional throws in bonus data like the IPs of those name servers. The footer at the bottom gives you query time, which resolver answered, and a timestamp. Gold when you're debugging. And reading dig output leads us straight into section 4, actually decoding what users see when DNS breaks. Here are the 6 errors that flood help desk queues. NX domain, whether it shows up as Chrome's site can't be reached or Firefox's server not found, simply means the domain doesn't exist, usually a typo. Survey fail points to a broken resolver or DNSSEC issue, so try 1.1.1.1 or 8.8.8.8. Error name, resolution failed is OS level, flush the cache, and bounced emails with 550 sender domain not found almost always trace back to a missing or misconfigured MX record. Memorize these 6, and you've handled the bulk of real-world DNS tickets. Now let's turn those errors into action. When a user says, I can't reach example.com, work these 6 checks in order. Each one peels away a layer. First, confirm whether anyone else can reach the site. Then ask, is the domain even in DNS? Is your resolver returning the right IP? Is that IP reachable? Is your local cache stale? And finally, is it actually the application itself? Stop at the first failure. That's your culprit. This single workflow handles roughly 95% of DNS tickets you'll ever see. With troubleshooting under your belt, let's zoom out to where most modern DNS actually lives, the cloud. Every major provider offers managed DNS, and the underlying protocol is identical to what we've been studying. What changes is the control plane, the pricing, and the integrations. Route 53 and Cloudflare lead the pack. Cloudflare for free global anycast. Route 53 when you're already deep in AWS. Self-hosted bind still exists, but in 2026, it's a niche choice for teams who genuinely need full control. Now here's a sobering truth. Classic DNS has no built-in way to prove an answer is genuine. Back in 2008, Dan Kaminsky showed how trivial cache poisoning could be. An attacker injects a fake bank IP, your client connects, credentials are gone, and nobody notices. DNSSEC fixes that by signing records cryptographically, building a chain of trust from the root down to the domain. In 2026, only about a quarter of TLDs have adopted it. But for banking, government, and anything financial, it really should be 100%. DNSSEC proves answers are authentic, but it doesn't hide them. And that's the next problem. Plain DNS travels in the clear on UDP port 53, meaning your ISP, the coffee shop Wi-Fi, anyone on the path can read every domain you visit. It's a postcard. DOT seals it inside TLS on port 853, while DOH goes a step further and tunnels queries over HTTPS on port 443. Indistinguishable from normal web traffic, which is why Firefox and Chrome quietly made it the default after 2020. Encryption protects the queries in transit, but DNS itself remains a high-value target, and senior engineers need to recognize the playbook. 6 patterns dominate: cache poisoning, where forged records get slipped into a resolver; hijacking, where attackers compromise the registrar account itself; amplification attacks that weaponize DNS for DDoS; tunneling, which smuggles data out inside queries; typo squatting with lookalike domains; and subdomain takeover of forgotten key names pointing at abandoned cloud resources. The good news: modern managed DNS providers handle most of these defenses transparently, but knowing the patterns is what separates help desk from senior. With the threat landscape mapped, let's pull this whole journey down to ground level. The actual tickets waiting in your queue. 4 scenarios: a website that's down for everyone, email that won't deliver to a partner, a server migration where old IPs linger, and an internal app that breaks the moment a user joins VPN from home. Each one has a clean diagnostic path. Confirm the symptom with DIG, isolate whether it's resolver, record, cache, or routing, then act. Work through these patterns a few times and they stop being puzzles. They become muscle memory. Now we level up. These 4 scenarios are what separates help desk from senior infrastructure work. A zero downtime migration hinges on one trick. Lower your TTL to 60 a full day before you cut over, so caches turn over fast when you flip the A record. Suspicious DNS queries from your servers? That's likely tunneling for data exfiltration, and TCP dump on port 53 is your first move. The Cloudflare versus Route 53 question comes down to where your workloads already live. And for GDPR, remember that anycast resolvers can answer from anywhere on the planet, which is exactly the problem compliance is asking you to solve. Before we close out, let's consolidate. These 16 terms are your DNS fluency vocabulary, the words that show up in every ticket, every architecture review, every postmortem. If you can rattle off what an FQDN, an SOA, a C name, and a glue record actually do, plus the difference between A and LA, MX and TXT, DOH and DOT, you're already speaking the language of a senior engineer. Treat this slide as your flashcard deck. Memorize it, and the rest of your DNS career gets dramatically easier. Now for the truths nobody writes down. First, when something breaks, check DNS first. The meme exists because it's right more often than it's wrong. Second, caching will make you doubt your sanity. The record is fine, the caches just haven't caught up. Third, your DNS provider is your availability ceiling. When Cloudflare blinked for 27 minutes in 2020, half the internet went with it. Fourth, DNS over HTTPS is a privacy win and an enterprise headache, because browsers can quietly bypass your corporate filtering. And fifth, the quiet one. Over 160 million domains lean on verisigns.com servers. If those ever go dark, so does most of the web. Internalize these five, and you'll think like a senior. And that's the journey. From a 1983 phone book problem to a cryptographically signed, globally distributed graph that quietly powers everything you do online. You came in knowing DNS turned names into numbers. You're leaving able to trace a query through the hierarchy, read the records, troubleshoot with DIG, and explain DNSSEC and DoH like a senior. Bookmark the RFCs, practice with the tools, and the next time someone says, "The internet is down," you'll already be 3 steps ahead. Welcome to DNS Fluency. Go build great things and help good humans.